Okay, so this lesson is looking at some different examples that we would do normally in the classroom, kind of on the whiteboard as a class. So this particular lesson has been set up such that you have in your possession all of the questions that we are going to be doing today. So make sure that you kind of print that out so you have a copy of this so that you can follow along and do the work in the book as well. But we're also going to be kind of talking about different things that you will need to know, whether that be for a test or for an assignment, that sort of thing. So the first part that we're going to be talking about is we're going to be talking about graphs, their shapes, and kind of what that means. So the first set of graphs that we have here are some position time graphs. These position time graphs are explaining to you where the object is. So when I look here at this particular first graph here, the object is moving farther and farther away as the time goes on. So we know that this is moving farther away from whatever reference point happens to be at the origin. All right, so I would look at this curve and I can see that it is curved upwards. So I would see that this is an exponential relationship. And that would make sense to me because my position is going to be in meters. So this is a meters versus seconds or time sort of graph. And this particular line here is showing is showing acceleration, and the acceleration is in meters per second squared, and there's where my exponential type relationship occurs. So the exponential, this object is accelerating. Now, if I was to look, oh, and it is also moving, sorry, away from the reference point. So if I was to look here at graph number 2, again, we got position time. Okay, we notice that this object, as time occurs, it starts really far away from me, it moves, gets pretty close, so it is moving towards the reference point. And then if I was to look at the slope of this graph, and so remember that slope is rise over run. And so slope is the rise. Okay, remember the rise is in this direction here. So the rise is displacement, run this direction here. So this is time. So in a position versus time graph, the slope is equal to velocity, right? Distance over time. So the more steep the graph is, like in this section here, the higher the velocity is, and then kind of as it straightens out, gets closer to zero, the slower the object is. So this object is moving towards me, but it is also decelerating. Okay, so the velocity, it starts out really fast heading towards me, and then it's slowing down as it comes towards me. This third graph here, again, same position, time, okay? It starts out really close to the reference point, so it is moving away from the reference point. And then again, if I was to look at the slope along this line, I would notice that it starts out steeper and it grows more shallow, so we know that this is decelerating. Okay, quite a different look to it versus the second graph there, where they're still decelerating. The question is, though, are they moving closer to me or farther away? All right, so this is, again, still a distance versus time graph, but now there's kind of these two portions to the graph. Okay, there's this first portion where the object starts really close to the reference point, and it is moving farther away. So in this first part here, we've got this away motion. Sorry, here we go, away. Then we can also see that it starts out quite steep and gets quite shallow till it is almost where it will actually exactly be zero. So it is not only moving away, but it is also decelerating. Then the object is moving towards me in the second half, And the line is getting steeper, which means that it is accelerating. Okay, or its velocity is getting higher. All right, again, position, time, starts out far away from me, moves closer towards me, so it is moving towards. Now, if I was to look at the slope of these particular points along here, I would notice that the slope is getting steeper, therefore it is accelerating. All right. So now we're going to change directions here a little bit. So I'm just going to change color here just to make that a little bit more clear. These graphs here are no longer position time graphs, but rather velocity time graphs. So the reason why we would graph a velocity is actually to do what is called straightening the curve. So if I was to look at an object that was undergoing this motion that's shown here in this graph, I would actually get, if I was looking at a position versus time graph, I would get that exponential relationship. The reason for that is because as time is going on here, the object is getting faster and faster and faster. Okay, so this graph is showing uniform acceleration. Okay, I know this because slope, again, like we said, is rise over run, where in this case, rise is a change in velocity and run, again, is still a change in time, and that is what acceleration is. Acceleration is a change in velocity over a change in time. So this graph is showing uniform acceleration in whatever the positive direction happens to be. So let's look at the next graph here. This graph, we've seen this portion of the line before. Okay, so we know it's doing uniform acceleration. Then we would notice that something happens here at 4 seconds. Um, Something happens, and what happens is the object stops accelerating and just travels at a constant velocity. Okay, of 10.0 meters per second. Okay, we know that there's no longer an acceleration because if this is slope, is a change in velocity over a change in time. Well, there's no change in velocity after 4 seconds. So it'd be like 0 over, we can say 2 here. So it'd be 0, okay, meters per second squared. All right, now, again, this next graph here kind of has this two parts, okay? We've got this part here, and then the second part here. So notice in the first part of the graph here, what's going on is the object is accelerating. Then in the second part of the graph here, it is decelerating. Note though, and this is the thing that students get confused quite often, the object is decelerating, but it has not changed directions. So there is no change. Oh my, sorry. There is no change of direction. Okay, there would be a change in direction if the line went into the negative side, or it had a negative velocity, or went from a positive to a negative velocity. Because there is no change in the direction that is associated with the velocity, the object hasn't changed direction at all. The object, though, does go from being at rest here to speeding up at its maximum velocity here, and then slowing back down to a stop there at the third point. So keep that in mind when you are trying to interpret graphs like these. It's quite hard. You just have to remember what your axes are actually representing. So for the second half of this particular video, what we're going to be doing is we're going to be doing a series of different questions. So we're going to start out here. You have these questions, like I said, in the little handout booklet there that I have scanned for you. So make sure that you've printed these off in order to follow along. um, here we go. The first thing that we should always do is draw a picture. Remember, I always expect kind of 6 steps for a calculation, and we give it the acronym PIC, CRAFT, DINNER for separate always. P for picture, K for what you know, D for what you don't know, your formula, your substitution, and then your answer. So first thing that I'm going to do is a picture. I've got a picture of a plane here, so I'm going to draw an arrow showing that it is traveling in a direction. Now, if I didn't have a picture, I could draw something very artistic, beautiful. Look at that. It's an airplane, and it is traveling in a particular direction. You don't have to be Picasso. I could state, look, there's an airplane as well. Okay, so it doesn't have to be anything beautiful. It just has to be some sort of picture. All right, so I've got my picture. Now what I'm going to do is I'm going to copy out the values that I have in the question. So including my units. So 23.6 meters per second. And then I have 13.0 seconds. And then I also have 43.0 meters per second. All right, so now I'm going to really look at my data booklet. And in my data booklet on page 2, there's a middle column along the top. And there it tells you what every single symbol in all those formulas mean. And it also tells you the units that are associated with that. So I would look for meters per second. Meters per second would tell me that this is a velocity. Seconds here tells me that this is a time. Again, meters per second tells me this is a velocity. Now I'm going to, so this is what I know. This is what the question is telling me. I have 2 velocities, so I have to differentiate between which one is the initial velocity and which one is the final velocity. So I'm going to read the question. The Red Baron is flying at 23.6 meters per second, begins to accelerate for 13.0 seconds. If his final speed is 43.0 meters per second, determine the acceleration. Well, it says his final speed, so this must be the final. The previous one of 23.6 must be the initial velocity. The question is now asking me for what I don't know, which is the acceleration. All right, so the next part of PIC, CRAFT, DINNER for separate always is going to be the formula. So I'm going to look again on page 2, and I'm going to look on the left-hand side of the upper portion of that page, and I would see the following formula of acceleration is a change in velocity over a change in time, and then it kind of breaks it down for me. Well, a change in velocity is the final velocity minus the initial velocity all over time, this change in time. So what I'm going to do now, this is my beautiful formula. Everything's nice and dandy. Why? Because the thing that I don't know is what the equation is actually solving for. So now I just need to do my substitution here. Okay, so of 43.0 meters per second minus 23.6 meters per second all over a time of 13.0 seconds. I go over here to my calculator, and I'm going to want to make sure that I put brackets for the first portion, just to make sure that my calculator is going to be doing this correctly. Okay, because really what this is saying is everything that is on the top there needs to be divided by the 13 seconds. So 23.6 here, got that brackets, all divided by the 13 seconds. And I've got an answer here saying that the acceleration is 1.49230769 meters per second squared. So now I'm going to ask myself, well, how many significant figures do I need to report my answer to? So I need to look back in the question. And in the question here, I am given the following numbers. This number here has 3 significant figures. I've got 3 significant figures here and 3 significant figures here. Therefore, my answer has to be in 3 significant figures. So this turns into 1.49. The 2 does not round up. Meters per second squared. All right, so now let's look at another question. The Starfleet shuttlecraft is moving at 1,600 meters per second when it begins to accelerate at negative 12.9 meters per second squared for 30 seconds. Determine its final velocity, magnitude, and direction. All right, So we already have this beautiful picture here, okay, and it has some things labeled in for us, and that's perfect. So I don't really need much more than that. So I'm going to skip down to writing down what I know. Well, again, I'm going to write down the numbers that are given to me with their units in the question. All right, so I have these three values. So now I'm going to look at what the units is telling me is associated with this particular prefix. So meters per second, that's a velocity. Meters per second squared, that's an acceleration. Seconds, that's a time. Now I'm going to ask myself, well, what is the question asking me for? So it says determine its final velocity. Well, this must be its initial velocity, so the question is asking me for the final velocity. All right, so now I'm going to look again in my data booklet, and I'm going to try to find the formula that has all four of these variables. And the great thing about it is the formula that we've already used. So acceleration equals final velocity minus initial velocity all over time. Now, I've kind of hit a snag, right? Why is that? Because the thing that I'm trying to solve is actually in my equation. It's right there. So what I need to do now is I need to rearrange the equation. So in order to get t out from under here, I need to multiply both sides by t. So I get t multiplied by a equals vf minus vi. In order to get vi away, I need to add vi to both sides. So I end up getting the final velocity is equal to time times acceleration plus the initial velocity. So now I just need to do some substitution here. So time is 30 seconds. We're going to multiply that by negative 12.9 meters per second squared. Then I'm going to add my initial velocity of 1600 meters per second. Sorry, I ran out of some room there. So final velocity is equal to, so here we go, back into my calculator. I'm going to need to put some brackets in here around this area here just to make sure that the multiplication happens first. So 30 times by negative 12.9 and bracket plus 1600. Enter. Okay, so 1,213 uh, 1,213 meters per second. Now I need to think to myself, does that answer make sense? Well, I've got a negative acceleration, which would mean that the object is decelerating, which means that it is slowing down. Now the object is moving extremely fast, so decelerating at a rate of 12.9 meters per second squared for only 30 seconds isn't going to make that much of a difference in the grand scheme of things. So I think that my answer is plausible. Now I'm going to look here. It says magnitude and direction, so it's still going to be in the positive direction. So that's perfect. But now I have to look for significant figures. So here I've got 4 significant figures, 3 significant figures, and 3 significant figures. So because of that, because of the fact that I've done multiplication, I need to report my answer to 3 significant figures. So I have 4 figures here. So what I need to do is I need to cut this down to 3. So I need to do some scientific notation. So I need to make a number that is in between 1 and 10 that is that has 3 significant figures, so that would be 1.21. Okay, so I have moved the decimal to this point here from its previous position here, which meant I jumped it 1, 2, 3 times, so times 10 to the 3, and it is positive 3. The reason for that is because the number is like the original number is greater than 1. So meters per second, and it's in the positive direction, and I can indicate that already. All right, let's go and do the next problem here, shall we? A racing car is moving at 22.5 meters per second when it accelerates to 46.9 meters per second in 3.44 seconds. Determine the magnitude of displacement. All right, well, I've got a car. Okay, he is already moving at 22.5 meters per second. He is going to speed up such that he is traveling at a rate of 46.9 meters per second, and the time that has elapsed is 3.44 seconds. There's a beautiful picture. All right, shows my understanding of what is going on. So I've got some values here. I've got 22.5 meters per second. Meters per second tells me this is a velocity. It says that it is moving at that speed initially, so it is its initial velocity. I've got a value of 46.9 meters per second. Meters per second says this is a velocity, and that would tell me that it is the final velocity because it accelerates to that speed. I also have the number of 3.44 seconds. Seconds tells me this is time. The last part of this is asking me for what I need to let it know, and I need to find out what the displacement is. So that's what I don't know. All right, so now I'm going to look here. Oh, shoot, I can't use the same formula because I don't have acceleration. So now I need to look for a formula that does not contain acceleration, but does contain the rest of my variables. And I would find the following formula in my data booklet. I would find that D equals VI plus VF all over 2 multiplied by T. So now, perfect. Question is asking me for displacement. I have displacement there. So now what I need to do is just fill in the rest. So I have 22.5 meters per second plus 46.9 meters per second, all divided by 2. And now I'm going to multiply that by 3.44 seconds. All right, so I've got 22.5 plus my 46.9 bracket. All of that is divided by 2. I'm going to close that up because all of that needs to be divided by 3.4. Oh, sorry, I guess I didn't put my multiplication in there. Multiplied by 3.44. All right, so enter. And I've got now a displacement of 119.368. So now I need to worry about significant figures. This would be meters. So significant figures here, I've got 3, 3, and 3. So my answer needs to be reported to 3 significant figures. So I could just do this by saying 119 meters. Note 3 does not round up. Okay, so 119 meters. All right. Next question. A racing car is moving at 20 meters per second. Sorry. When it accelerates at a rate of 4.55 meters per second squared for 8.66 seconds, determine the magnitude of displacement. Car. Moving along. Okay, starting at 20.0 meters per second. He accelerates, okay, for 8.66 seconds. The question is asking me how far is this? All right. Well, I've got some values. I've got 20.0 meters per second. I've got an acceleration of 4.55 meters per second squared. I've got a time of 8.66 seconds. Meters per second velocity, this is the initial velocity at which the car is moving. 4.55 meters per second squared, well, that's acceleration. I know this because it's meters per second squared. 8.66 seconds, well, that is obviously time. And then the question is asking me for what the displacement is. All right, so I'm going to look for a formula that does not contain my final velocity, and I would look in my data booklet, again, page 2, and I would find the following formula. So VIT plus a half AT squared. Okay, so what this is saying is the displacement is equal to the initial velocity times the change in time. Oh, sorry, this should be plus a half times the acceleration times time squared. So what I need to do now is I need to substitute in my values. So I have 20.0. Oh, hold on, I'm going to need some more room here. So 20.0 meters per second. That is going to be multiplied by my time of 8.66 seconds. I'm going to add that to a half times the acceleration of 4.55 times 8.66 seconds squared. Sorry, this should be meters per second squared. Okay, so putting this in my calculator, I've got two main areas. So I've got the first one of 20 times 8.66. Then I need to add to that, okay, a half. A half is represented by 0.5, okay, rather than doing 1 divided by 2. So a half, or 0.5, times the acceleration of 4.55 meters per second squared, multiplied by 8.66, and then what I can do is I can just square that number by pressing the squared button. And bracket, press enter, and I get a value of D equals, sorry, 343.81499 meters. I'm going to look again for significant figures. Here I've got 3, 3, and 3. So I need to report my answer to 3 significant figures. So I'm just going to do this by rounding up here. I've got 344 meters as an answer. All right, so let's do the next question here. Homer drops a donut from the top of the reactor building. How far will the donut drop in 1.5 seconds? So they summarized the data here for us already. Note it says drop, so the initial velocity is 0. Acceleration is 9.81 meters per second squared, and if you didn't know that already, well, it is actually in the astronomy data on the bottom of page 2. It says the average acceleration due to gravity on the Earth's surface, and that's 9.81 meters per second squared. Distance is what it's asking me for, and it gives me time. So I'm going to look for a formula that, again, does not have the final velocity, and I'm with the same formula here of, D equals VIT plus a half AT squared. Well, I need to solve again for D. That's perfect. Now, one of the things that I want to bring your attention to here is this initial velocity is 0, which means that this value here is 0. And anything times 0 is 0. So I can cancel this entire value out. Just to simplify, to get D equals a half AT squared. Now note that this only works if the initial velocity is 0. If the initial velocity is anything more than 0, then we can't be using this formula at all. All right, so here we go. D equals a half AT squared. So a half times 9.81 meters per second squared times the time of 1.50 seconds, and we need to square that. So in my calculator, I'm going to do 0.5 times 9.81 times 1.5 squared. Enter. Oh, what did I put in wrong here? Oh, sorry. Delete. There we go. 0.5 times 9.81 times 1.5 squared. Enter. There we go. And I get a value of, the distance is 11.03625 meters. So if I was to do proper significant figures here, I've only got this one here of 3 significant figures. So this would be 11.0 meters. Okay, so let's move on here to another problem. Calvin and Hobbes fire a rock straight up with an initial velocity. Okay, so in this one here, I'm really going to want a picture. So he is throwing a rock up into the air. Okay, straight up with an initial velocity of 46 meters per second. How high is the rock after 4 seconds? So note here, this is where vectors become really, really important. So my initial velocity there is 46 meters up, and in this case here, I'm just going to say that up is positive, down is negative. So what I'm going to do in order to figure this out is I need to give acceleration a negative value. Okay, so again, we're using the same formula here of d equals vi t plus a half at squared. So my initial velocity of 46 meters up was 46.0 meters per second. I'm going to multiply that by 4 seconds. Here we go. 4.0 seconds. Now notice this is a positive value here, okay? And that is going to be added to, sorry, this is multiplied by here, okay? Added to a half times the acceleration of negative 9.81 meters per second squared times, again, 4, and I'm just going to put square, 4 seconds squared. So here we go, bracket, so 46 times 4 bracket plus, we've got a half, so 0.5 times negative 9.81 times 4 squared. All right, enter, and I've got a value of distance 105.52 meters. Now, we need to look at significant figures. So here I've got 3 significant figures, 3 and 3. So my answer needs to be to 3 significant figures. 5 rounds up, so 106 meters. It is very important that you put the negative or the negative 9.81 in there, just because it shows that the object is actually decelerating. So that's very important. Okay, so what we're going to do now is I'm going to stop the video, and the next questions are going to be questions that are on kind of the photocopy pages out of the textbook, and they're going to be some of the circle questions as well as some of those that aren't. So what I would like you to do right now is take some time in order to do some of those questions, especially to do the circled questions that are on there, and then to do kind of the first, let's do the first 7 on the page 53 out of that photocopied booklet. And then what you should do then is click on the next video, or the second video in this package will be showing you kind of the next step, or the questions that are the 1 through 7 on that page. Thank you for watching. Make sure, again, like I said, that you do the practice first before you follow the next set, just to make sure that you're doing these right.